not, let's start. All right. So today we're going to continue our discussion of representation theory of the Poincare group with discussing spinors. In particular, actually, this is perhaps going to be very useful to you guys, no matter you are condensed matter theorists, high energy theorists, or what. We're going to talk about what is a Weyl spinor, what is a Majorana spinor, and what is a Dirac spinor. The existence of such particles or such fields is imposed on you by the symmetries of the theory, which is the Lorenz invariance or Poincare invariance, right? Okay, so we're going to go through that. Let me start by reviewing lecture 10 to make sure we're all on the same page. So we talked about the Poincare group representations. The Poincare group is Lorenz transformations, lambda mu nu, and translations. You could package them this way. Here is the translations, and here is the Lorenz transformations, OD, 1. The group of orthogonal matrices, D plus 1 times D plus 1 dimensional matrix, D plus 1 times D plus 1 matrices that preserve the Ada mu nu, the metric -1, 1, 1, 1, 1. Right? That's the definition of the group. Well, actually, orthogonal group does that. Then we said that in specializing to 3 plus 1 dimensions, because the representation theory depends on the dimension, and that's a dimension of interest for us, we found that there are parity and time translations as discrete subgroups, Z2 subgroups of the Poincare transformation, Lorenz group, actually. So there are 4 disconnected parts to the this Lie group. We restricted ourselves to the restricted Lorenz group. This is the component, the part of the Poincare group, or the Lorenz group, that is Lorenz group, which is continuously connected to identity. So the determinant is equal to 1, and lambda 0, 0, the 0, 0 component of the Lorenz transformation, larger or equal to 1. Are there questions? Okay. All right. So under such, so we discussed in detail when we're discussing symmetries that our fields are going to transform in representations of the Poincare group. So to each Poincare, and representation was basically a map from the group to matrices, such that group multiplication is represented as matrix multiplications. So we said that now that it's simply that this thing is connected, the component, we focus on the component that's connected to identity. We could expand our group elements near identity in the tangent space near identity and look at the Lie algebra. The resulting Lie algebra has could be classified, could be organized in terms of 2 sets of generators. P mu are the generators of translations, otherwise known as, well, momenta, right? P0 is Hamiltonian and P are regular momenta. And J mu nu are the Lorenz charges. We said that the charges satisfy the Lie algebra. So here's the Poincare algebra. The translations commute. Well, this is what the so the translations and Lorenz transformations do not commute, and Lorenz transformations are non-commutative themselves. To write down the charges in more familiar language, we said that you could take this J0I and call that Ki. These are your boost transformations. There are 3 of them. The I index runs from 1 to 3. And Jij is a basically 3 by 3 matrix, but it's anti-symmetric. And you could write it in this form to get the angular momentum. There are 3 of them labeled by K. Epsilon Jk is the anti-symmetric tensor. Then we said that now that we wrote it in this familiar form, focusing on the Lorenz group alone, right? So let go of the translations for now. You could construct such combinations. You add Ji plus minus Iki, right? So you add boost and angular momenta in this particular combination. You're complexifying your field, right? Your transformations, and define these. Why do you do that? Because that way you could decouple this algebra. You could block diagonalize this algebra into two copies of SU2 algebra. These are the standard SU2 relations, and the generators, they commute with each. There are two uncoupled copies of SU2. So this is at the level of the Lie algebra, the tangent space near identity, right? Good. So it's important to remember SU2 cross SU2 as a Lie group is not the same thing as Poincare transformations we're looking at, right? At the level of the Lie algebra, the tangent space are the same, but the whole groups are different. They're locally the same, basically. All right, any questions? Then we continue that conversation by saying that, okay, so we have no central extension for the Poincare group. The reason is that Poincare group, well, Lorenz group is SOD, 1. Identity is not in the among the generators. You cannot centrally extend it, right? Remember, all the S algebras were like that. Special ones were like that because there were SOD, 1. All the generators were traceless Hermitian. Sorry. And also, but the point is that it's not semi-simple, so it has projective representations known as spinors, right? So we said that we could classify the representation theory very simply because you guys know the SU2 representation theory. There are SU2 representation indices. These are spins, left chirality spin, right chirality spin, and J left and right run from 0, half integers, right? So the half integer ones, half, 3 halves, 5 halves, 5/2, these are projective representations as opposed to regular representations, which are 0, 1, 2, 3, and such, right? This is clear even in the case of SO3 rotations, right? So in the case of SO3, as you go around the circle and come back, the projective representations become a minus sign, as opposed to the actual representation that you go around and you get identity. All right, we said that that's related to them being to observables in quantum mechanics. All right, so the 0, representation is a scalar. It has 1 degree of freedom. It's a Lorenz scalar. The half, 0 is a left-handed Weyl spinor. We use this notation for it. The 0 half is another Weyl spinor, the right-handed one. They each have a 2 degrees of freedom, and we usually use this notation to distinguish between left chirality and right chirality. Then we have half representation, V alpha alpha dot. This has 4 degrees of freedom, and we said this is nothing but the Lorenz vector. That we rewrote this in terms of the standard notation for the four component notation of the Lorenz vector using these sigma mu alpha alpha dot matrices, which were basically they were the Pauli matrices with the identity included. So you're going to work out an example in your homework related to this because it plays a big role in the representation theory. All right. Then we said that if somebody hands you 2 left-handed Weyl fermions, you could construct this using epsilon tensor. You could construct this Lorenz invariant, and you could view this epsilon ij alpha beta as some sort of a spinor metric. That is not a terribly meaningful, well, it's a very abstract concept. Don't take it very literally. It's not a space-time kind of metric. It's just an internal thing. And then always think of this as a 2 psi alpha or psi bar alpha dot as a vector with 2 components. So that's where we stopped last time. Sorry. Today we're going to talk in more detail about Lorenz transformations of spinors. We're going to introduce, well, we already introduced Weyl spinors. We're going to introduce Majorana spinors and Dirac spinors. So here's a little warning. the notation terminology could vary from place to place. I'll try to explain all the, well, a few of the possibilities or conventions and notations and terminology that people use, okay? We will talk about action for spinors, local action for spinors. And then we'll talk about the Dirac equation, Weyl equation, Majorana equation. Now, why are we doing all of this? In the past, I told you that when in the next part of the course, when we talk about representation theory, irreducible representations are going to become particles coming out of fields, right? The field picture. The point here is that comes out of the representation theory of Lorenz group, this observational thing we had seen in our universe, that particles come with antiparticles. So the detail of this representation theory is important. I'm walking through it, walking you guys through this math, because this is how we understand particles versus antiparticles, right? So antiparticles in relativistic physics are sort of imposed on you, and they have to be there. They just have to be there, and this is where they come from. If you don't want to, if you just want to accept antiparticles are what they are, then you're missing out on this internal structure. There's a reason for them. All right, this is the physical picture I want you guys to keep in mind every time you find yourself lost. Why are you doing this? This is part of the reason, one of the main motivations for this. All right, any questions? Okay, so let's get started. A little bit of review. Let me just give you a little disclaimer. Well, not a disclaimer, but something for you guys to keep in mind. I told you this before. Working with indices requires a lot of practice. You could easily get yourself confused, and there's just so much we could do in class, right? So you will have to work out these examples to get some sort of sense for these type of calculations. I'll try to, every time I try to come back to the original picture to make contact from between this abstract notation and what the whole representation theory was. But if something is confusing, at some point you lost track of things, just ask, and we're gonna try to reorient ourselves and make sure we're not lost. All right. Lorenz transformations are what we're focused on. Lorenz transformations act on fields. Now, a field, for example, a chiral fermion, a left Weyl fermion or right Weyl fermion, could be viewed as psi of A of X. This A or alpha is an index that runs from 1 or 2, or it could be some sort of funky representation with a larger dimensional thing. So the index A could be running on over many indices. In the Hilbert space, these are symmetries, so they act like unitary transformations. Sorry, but fields transform as representations of the Poincare group, and here are the representations: D of BA alpha of lambda. What I want you guys to keep in mind is that this is how things transform. We're talking about space-time transformations. Of course, the space component of it transforms and the field transforms, right? So today I'll just have one slide on how this, reminding you how the space part of it transforms. And then to simplify our notation and discussion, we'll just drop that and focus on this bit. All right? But keep in mind, every time you're talking about such transformations, always there's a space part to it. So the space part of it is pretty simple. All right. You take this unitary, we did this before, you expand it and around the identity, and you discover these self-adjoint operators. They're self-adjoint because this guy is a unitary in the Hilbert space. These are the generators of charges. These are charges, generators of the transformations. So if you take the commutator of one of these charges with your field, there will be two parts to it. This equation is an infinitesimal version of this equation, right? There will be the part that comes from the spatial part of the transformation, this bit. And then there is the part that comes from the representation. the part that comes from a spatial part of the representation that has to do with x going to lambda minus 1 of x is generated using this differential operator. This differential operator is the thing that applies a Lorenz transformation at the level of points in space-time, right? For example, if you have a scalar field, even though this part of the transformation representation part of it is trivial, you still have this bit. So for a scalar field, you have this part of the transformation still, right? This is the part that we're gonna ignore for now and focus on the representation. But I just wanted to remind you guys again what I'm sort of hiding, right? Just to simplify our notation. So with that said, we want to focus on how lambda mu nu Lorenz transformations act on Weyl spinors, say left Weyl spinors. So because Weyl spinors are two-dimensional representations, so we're gonna talk about 2x2 matrices, right? We have constructed them before, but let's just go over it step by step. Before telling you what these matrices are, let's just see what we expect. Of course, this alpha index is the index of this the representation, right? So it's going to be some sort of a matrix with alpha beta indices acting on it, and this is the notation I'm going to be using. Index-free notation, right? Now we know that this is the upper psi alpha, chi alpha, with psi alpha raised using this epsilon tensor, right? Is a Lorenz scalar, so it should transform like this. So if chi alpha lower transforms like by multiplication of the representation on the left, then psi alpha upper will transform with multiplication on the right of s minus 1. Right? That's just because this guy has to remain invariant. Good? Is that part clear? If that is a little bit confusing, you could try to work out this identity, convince yourself this identity is correct, and then using this identity, you could directly work out the transformation laws for psi prime alpha. Good? Any questions? Now I'm going to mention a point about, so similar story holds for right-handed Weyl spinors, and I'm going to use S bar for the representation matrix for the representation. Now notice that I switch from going from left-handed to right-handed spinors. I switch my notation, my convention. There's a reason for that. This is a convenient notation, and here for the upper index one, I use psi S bar. And for the lower index one, I use S bar minus 1 of lambda. It's not too surprising. You could easily convince yourself this is a good notation, but I'll try to comment on that. All right, so this is, if you know the matrices S, this is how the upper and lower spinor in the spinors with upper and lower indices transform, right? The left Weyl and right Weyl spinors. Are we good? Questions?
So both this upper and lower thing are both represent R100 Weyl spinors.
Yeah, they're the two. You have 2 degrees of freedom. It's the same thing as like if you were to make a comparison with Lorenz group, sorry, with say vectors under Lorenz group, it's above V. Covariant and contravariant vectors, right?
Okay.
V upper U, V lower U.
That's it.
Yeah. All right. Now, let's talk about what these representation matrices are. You already know these representation matrices, sigma mu nu, sigma bar mu nu. But let's just work it out a little bit more. So we just said how the left and right transform. Let's pick a Lorenz vector, which is a representation half-half, half left, half right, for of the SU2 comma SU or the Lorenz group. So V alpha alpha dot that we say Lorenz vector will transform by S of lambda on the left and S bar of lambda minus 1 on the right. We said that the way you connect this spinor notation, spinor representation of a Lorenz vector with the standard V lower is using these sigma mu alpha alpha dots, right? Which were basically related to the Pauli matrices. Now, what is interesting is that this sigma alpha as a matrix, so now these are 2 by 2 matrices. Sigma mu is a 2 by 2 matrix. If you apply S bar of this, it transforms like a Lorenz vector. This is how it transforms. Well, it's just simply what we mean by saying that this V alpha alpha dot is Lorenz vector. It's convenient to define the sigma bar of mu with a minus extra minus sign here. That sort of is the inverse relation for this this first line. So the first line I'm writing V alpha alpha dot, the spinor representation in terms of the vector, and this is the inverse, right? So V up the standard vector representation is written in terms of the spinor half half. All right. Now, using this, I can define anti-symmetric tensors sigma mu nu alpha beta and sigma bar mu nu alpha dot beta dot. So getting used to these expressions and why we have these expressions as just take some exercise, homework, and just some playing around. But the point is that you're gonna play with them in one of your homework problems, but you're gonna learn that these anti-symmetric tensors, they satisfy the Lorenz algebra, and they are the generators of this. They are precisely the representation matrices, this 2 by 2 representation matrices for the left and right Weyl fermions, Weyl spinors. So
hello.
Yes.
Hello, Professor. Why here we define the first component is the I identity?
Why is there an I here, are you saying?
I mean, for the sigma mu, the first component is the I identity. Does the I will influence the calculation?
It's very crucial, this I, yes. It's very crucial, this I, yes. You're gonna get some sort of intuition for this notation once you work out the homework. For now, just accept it as a fact that is you need an I here if you want this sigma u to transform like a Lorenz matrix. Sorry,
okay.
Lorenz vector.
Okay,
but you're gonna discover why. Of course, a lot of times these are conventional, meaning that you could get rid of that I at the cost of redefining a bunch of things, pushing this I around. But this convention is pretty standard. So these are our representation matrices. As you can see, they are 2 by 2 matrices, right? Alpha, beta are indices that run over 1 and 2. This guy generates Lorenz transformation on the left Weyl spinor. This guy generates a Lorenz transformation on the right Weyl spinor. And I wrote them in terms of this thing that was generating Lorenz transformations on the vector. So this, going back to the this discussion that we had here, we had this representation matrices. So that was at the level of the algebra. These representation matrices, if you expand them, you're going to discover these generators, right? So what did we do? We wrote down explicitly the generators of Lorenz transformations as how they act on left and right Weyl spinors. These are 2 by 2 matrices. Sorry. Recall that every Lorenz transformation has a mu and nu index. That's why these sigmas and sigma bars have a mu nu index. Good. All right. Actually, this is a good moment to pause. Is this part clear? The important thing in this story are these sigma and sigma bars. These expressions are how you apply Lorenz. These are the generators of Lorenz transformations written in the Weyl spinor, left and right Weyl spinor representations. All right, very good. Now that we know what these representations are, let's try to write down an action using these, right? So these are our fields. We want to write down an action. So to simplify my life and not carry around a million indices, I'm just going to use this notation, index tree notation. When I write psi chi, what is meant is psi alpha up, chi alpha down. It's important. Recall that you can't change the order. If this is not the same thing as psi alpha lower, chi alpha upper, because we commented on that because of the the Grassmannian nature of these variables. And similarly, this is how we define the right-handed ones. These are singlets. These are Lorenz invariant quantities. So you could write them, include them in your Lagrangian, because Lagrangian density for local action, we call the principle of locality. It should be an integral over something local, and the local thing better be a Lorenz singlet. Sorry. So these have the flavor of a master because they're second order and they're filled to squared-ish, right? So we're going to get that. This is what expression we can write down in terms of purely left Weyl fermions or right Weyl fermions, right? Now we could write down Lorenz invariant expressions using mixing left and right spinors. So how do you do that? Well, you can put this chi bar, which is a right Weyl spinor, psi, which is a left Weyl spinor, stick in the middle, sigma view. Why is this Lorenz invariant? Well, recall how these guys transform. This guy transforms like S lambda minus 1 on the left. This guy transforms like S bar lambda on the right. And then the middle part is transforming as what sigma mu transforms up to this. So this equation, if you don't know where it came from, you've seen it here. So this is the equation that tells you how sigma use transform. Putting all of this together, you learn that this guy, you can write down Lorenz. Oh, sorry, what did I say? I misspoke. From this, you learn that this is a Lorenz vector. I misspoke, sorry. This is a Lorenz vector, right? Because it transforms like a Lorenz vector. So if you want to get something Lorenz invariant, you could just put a del mu derivative in between the two. That will ensure you get something Lorenz invariant. You might be tempted to put a bar here, put a right-handed Weyl fermion here and left-handed Weyl fermion here. But it's easy to convince yourself using the algebraic relations of the representation we've gone over that will not be a new term. That will be just a minus. It's the same thing with a minus sign. We're going to use that in simplifying our action expression for the action. This is the Lorenz invariant that we could write down that couples the left Weyl mode and the right Weyl mode. So what did we do? We constructed things that look like left mass terms, right mass terms, and a left Lorenz invariant term, which is first derivative. It has one derivative in it, right? Those derivatives are important. They're physical. Recall that for a scalar field, or most of the theories you've worked with, and your Lagrangian density is second order in derivatives, right? That has to do with the fact that your equations of motion are second order in del T and del I. Good, hopefully that's familiar. Del mu phi, del mu phi. But here we're just writing expression which is first order in derivative. That has important dynamical consequences. Any questions? All right. So now let's take this Weyl spinner, and again, these are the parts that I have to, I was telling you have to play around and work out examples to get used to. You could take this expression, write it in this form with a minus sign because of just the equation, because of this identity. Just because of this identity. Use it similar to that identity, you could write this Lorenz invariant term we wrote down this way. Now, you could complete the derivative as a total derivative and write it this way. You learn that the following combination is a total derivative. So it doesn't really help you to add such terms to the action. Whereas if you put a plus in the middle, you're going to end up with an action which is called the Weyl spinner action. Good. Here's something funky is going on, which could cause a lot of confusions. What am I working with? Well, there are actually many comments I should make here. Let's, for a second, think about, go one by one. Here is your psi, and here is your psi bar. They are independent left and right Weyl fermions as I've written this down. d4 of x. If you vary this action with respect to psi or psi bar, you get the Weyl equation that looks like this. Right? The Weyl equation tells you you could have a single Weyl mode, but to write down this action, we needed two of them. Right? So the equation of motion could be written for a single Weyl mode. But to write it down as a variational principle, I needed two of those guys coupled in this particular way. That's sort of why sometimes, well, we'll discuss that. We'll discuss that. So that's comment number one. Comment number two is something that we discussed in the last lecture. Here, what we are dealing with, we constructed all of these out of a representation theory of SU2 cross SU2. That is a spin version of SO4. So this is for theory, the field content, the spinners I'm writing down. This action is really an honest to goodness action for theory that has SO4 symmetry. This is the symmetry group of a space which is four-dimensional, well, actually S3, three-dimensional sphere, not flat space. I don't know how you count, but anyway, right? Our Lorenz group was SO3, 1 and not SO4. So on the left, I have what we should have. What we physically should have, which is a Lorentzian theory where the metric is -1, 1, 1, 1, and that the space is R3, 1, as opposed to what's called the Euclidean theory, where the metric is 1, 1, 1, 1, and the space is R4. So what I've written down here actually has a name in physics. This is a Euclidean action. It says these are spinners for Euclidean theory. If you look at the projective representation of SO4, that is spin force, literally two copies of SU2, whereas the spin representation of 3, 1 is SL2C that we said is not SU2, SU2. This is actually very important. This is the distinction between the two is where all this antiparticle, Majorana, and all of that come in. All right, let's pause here. What happened? I wrote down this action based on just the SU2 cross SU2 representation, right? Locally, that representation theory is the thing that I care about, but my group globally is different, right? So what I should be working with is SL2C. So I'll tell you what the distinction is. Here is a table to have in mind. On the left, you have SL2C, the representation theory of 3 plus 1 dimensional Lorenz group. On the right, you have the representation theory of the Euclidean theory. So this is the Lorentzian, this is the Euclidean theory. The reducible representations are labeled the exact same way, using J left and J right of SU2. You have left Carl left Weyl fermion, right Weyl fermion. Left Weyl fermion, Spinors, right Weyl Spinors. Now there's a distinction. In the case of the Euclidean theory, SU2 cross SU2, what you have is a pair of independent real spinors. So you have a left Weyl spinor, these are real, so it's a vector with two real variables. And then this is the left, and then the right is another vector with two variables that are also real. The distinction between this and the Lorentzian theory is that you have your left mode, Weyl mode, is actually complex. It's a vector of two complex fields. And the right and left are no longer independent, but they're complex conjugates of each other. Think about it in the same language as, let's say you have two scalar fields, phi1 and phi2, and you can write down the action for phi1 plus the action for phi2 as phi1 and phi2 are independent, or packaging them as phi1 plus I phi2 and working with the field and its complex conjugate. So this is precisely, this I is precisely the origin of the story. This I here is why there is such a distinction, right? So the SU2 variables have this extra I thing. Anyway. All right, coming back here. So what does all of this mean for the Lorenz group? It means that when you are looking at the Lorenz representations of your Lorenz group, you still have the left and right Weyl nodes, spinors, but each of them are complex two-dimensional vectors, and the left and right are complex conjugates of each other. So you have this relation, but more importantly, the representations are related. S bar of lambda, in the case of Euclidean theory, had nothing to do with S of lambda. You could independently apply Lorentz transformations, but here they're actually related to each other. One of them is the complex conjugate dagger of the other one, -1. Is this point clear? I should pause here. All right. We want to write down an action for a Lorentzian theory. The action I wrote down here was for a Euclidean theory. That's no good for us. We want a Lorentzian action. Now, we need an action that's real. Does anyone know why? Why do we need a real action? Well, the answer is very simple. If you, from the action principle, if you go to the Hamiltonian picture, you want a Hamiltonian, which is, all right.
Summation?
Thank you. All right, very good, thank you. So that's important for unitarity. Now, now that we are dealing with these variables that are complex, we have to keep in mind complex conjugation. So we wrote down this expression in our as a Lorenz invariant term in our action. So let's see whether it's real or not. Take the star of it, take a complex conjugate of it, and you discover you could write it in these two forms. If you take the chi term that we use to write the mass term, and you can take the star of it, you get chi dagger. All right, so let's try to write an action. Here's the action we're going to write down. If you add, but by the logic up here, if you add these two terms, you're guaranteed to get a real action. Just take the star of the both terms and they cancel. Well, the imaginary part of them cancel. And then to make sure that this term is real, you have to add m chi plus m star chi bar. Here, m is a complex mass. It's a complex variable you could have there. Such a mass term is called a Majorana mass term. And such an action describes a Majorana spinor. So the terminology could be confusing. I'll try to clarify that as we go ahead. You already knew what a Weyl spinor was, right? I wrote down an equation of motion for the Weyl spinor. I wrote down something that looked like an action, and but it required a pair of them, and there were some sort of issues regarding the distinction between the Euclidean and Lorentzian theory. But there was an equation of motion. Here I can write down an action. There's a Majorana mass term that's allowed. Basically, in short, keep this in mind. If there is a mass term, this is a Majorana. Often it's called Majorana spinor. If there is no mass term, you can view this as two copies of Weyl. But we'll go ahead. So you take this action, you vary with respect to chi dagger, and you get the Majorana equation. Sometimes this equation is called Weyl equation. I apologize. That's just how things are. People call them different things. Now, what's important, remember, so this is the extra term compared to what we call Weyl equation, the mass term. Right? Now, the mass couples left and right Weyl spinors. The mass is forbidden in a theory that you only have left Weyl spinor, right? Or in a theory that you have a symmetry like this. Hopefully it's clear why it's forbidden, because the action doesn't remain invariant under such a transformation. So if these are charged under U1, right? Remember, chi is now a complex vector field, so it could be charged under U1. There could be a U1 transformation, but this term spoils that symmetry. The rest of the action has that symmetry, but this term spoils it. So if there is a principle in your theory that says there should be a U1 charge, if these spinors are charged under a U1, so they're coupled to some sort of a gauge theory photons. If these spinors that are going to become your fermions are going to be coupled to some photons, such terms are forbidden. Now, let's take a left-handed, a complex left-handed and a complex right-handed spinor, chi and chi bar. I write them as chi and chi bar, but they are independent, complex L and R spinors. They are not the complex conjugates of each other right now. So what is the action for them? Precisely the actions that are wrote up here. You can write down this action for chi. You can write down this action for chi bar. So you have two copies of this. But you could have a term that couples these two guys as well. So each of these guys, so the first term has m chi, a complex m call this chi. So there's a complex mass here, m chi in the first term. And then the second term has m chi bar. These are the Majorana mass terms that I said that they're forbidden if you have some sort of a U1 symmetry. But you could write down another term if you have two of these Majorana modes that couples them. This is a brand new mass term that's allowed. It's M prime. It's called a Dirac Master. So here are your equations of motion for this theory with a left complex Weyl and an independent, sorry, I should, Majorana and an independent right one. Here are your equations of motion. So they're coupled. They're coupled to each other. I'll try to summarize it at some point. You might find yourself confused about this notation. Once we describe Dirac, a lot of this becomes simple. Well, simple. It's a good, there's a nice summary. All right, so recap. You knew from the last lecture what a Weyl spinor was. We wrote down an equation of motion for the Weyl spinor. We wrote down an action that involved a pair of them, and the action was invariant in Euclidean theory. Then we wrote down an action with allowed mass terms for what we called Majorana mass for these guys. The equation of motion of the Weyl was shifted by mass term. And this mass term couples left and right. Finally, we took a pair of independent pair of complex left and complex right, wrote down an action. There was a brand new mass term that was allowed. We called that the Dirac Master. Good. All right. Very good. So it's finally time to go to the four-dimensional notation. What we're going to do is that we're going to take this action and write it in a more familiar language in Dirac notation. So what do we have? We have a pair of vectors, two-dimensional vectors, each of which are complex. So we're going to package them into a four-component Dirac spinor. The top two components are the left complex Weyl spinors. The bottom two components are the right complex Weyl spinors, or Majorana. This is often called a chiral basis. It's a very convenient basis, but Dirac spinors are sometimes written in other bases. I apologize, it's confusing. This is a very convenient basis. So with this, remember that to build our representation theory, we started with this sigma mu's and wrote down sigma mu nu's. Here, if you're working with the Dirac spinor, you could package, because you have a pair left and right complex at the same time, you could package them in terms of a 4x4 matrix called Dirac. These are Dirac matrices, right? Which has off diagonal upper here, the 2x2 sigma mu, and here lower sigma bar mu. Dirac matrices map left-handed to right-handed spinors because it's on the off diagonals.
One question.
Yes.
So I feel, and I think so, but you might correct me. This one half representation that we talked, it was like a Lorenz vector representation.
Correct.
How is it different from this Dirac representation, which would have also like this left and right hand?
It's not related at all. It's just sort of like a, I guess, it's a coincidence in 3+1 dimensions that, well, I'll say that in a bit. It's not totally unrelated, but it's something that works out in 3+1 dimensions. It's in 3+1 dimensions that you could write down your Lorenz transformations and representations in terms of two pairs of SU2, right? And if you have a left and a right, or a vector, right, it's going to have four of these guys. So if you were saying like 4+1 dimensions, right? A vector will have 5 components, right? There's no way to break down 5 components as a pair of like 2 vectors or something, right? So these features are dimension dependent. This phenomenon that we saw is something that works out in 3 + 1 dimension. It has to do with representation theory and how. Good.
Yeah.
All right. So I'll actually comment on that. Now, these Dirac matrices, they're 4 by 4 matrices. So keep in mind, this mu index runs over 0, 1, 2, 3. So it's 4 indices. But each of the matrices are also 4 by 4. The 4 by 4 of matrices are internal directions. These have to do with the spinor representation. I guess that was the comment I was just making. These guys satisfy what's called the Clifford algebra, which is the anti-commutator of the Dirac matrices is 2 times the Lorenz metric. Well, sorry, the metric space-time metric, Minkowski metric, times identity, the 4 by 4 identity in the spinor representation. Now, using this Clifford algebraic relations, we can, so let's recall what, this is the action we're gonna write, and what we're gonna do is we're gonna take this action and write it in the 4 component notation of Dirac, right? So what you do is, here are the 2 of the terms that you had in your, 2 sets of terms that you had in your kinetic parts, right? You could write them in terms of psi dagger, psi, these are 4 components on the left. So all this curly psi is my attempt to write down a 4 component thing, right? Whereas on this side, these guys are 2 components, right? And sigma 0, gamma 0 is gamma 0. So mu runs over 0, 1, 2, 3. So these indices are hopefully clear. Having said all of this, there is some sort of a homework problem you're going to work out to see that this whole action, for a second, ignore the mass terms. The kinetic part of this action could be packaged in terms of the Dirac action. So the kinetic part of the action is Dirac action. Now, how do these Lorenz transformations act on a Dirac spinor? Dirac spinor is this 4 component thing. Well, this is the representation of the left part. This is the representation of the right part. You have to put them on the diagonals, right? But because we're in SL2, SO3, 1 and not SO4, they are related. These are complex representation, and this guy is the dagger of the other one to the power of -1. Now, how are these related to the representation of Weyl fermions I was just telling you about? Well, these representations, you look at their generators, the sigma tilde. These are 4 by 4 matrices, right? Complex matrices, and they're nothing but block diagonal of the representation of the left Weyl fermions, the action of the Lorenz transformation of left Weyl fermions and the right Weyl fermions. Remember, this is acting on a Dirac spinor, which is left and right Weyl modes. Now, if you want to know if there's an elegant way of writing these down, all in terms of Dirac matrices, yes, there is, and here it is. As a matter of fact, this whole song and dance we've been doing with Weyl spinors and these representation theories is something that was very specific to 3 + 1 dimensions. We started with Weyl representation. It was a feature of 3 + 1 dimensional space that you could write down as spin 3, 1 in terms of a pair of SU2 spinors, right? And we walked you through all of this, but the end result of representation theory Lorenz group is really in terms of Dirac matrices. It's this this Clifford algebra that generalizes and builds representation theory in various dimensions. In 3 + 1, we're in this lucky situation that you could relate it to the SU2 representations you knew about already. Good? So we wrote down the kinetic part of the Lagrangian. Now, what about the Dirac Master? So for a second, imagine that there are no, these Majorana masses are 0. So we just want to work with this M prime. So I'm going to set Majorana masses to 0 and when I work with M prime, here's just an identity you could work out. That tells you that your Dirac action, you could simply add master to your for your Dirac field, your Dirac spinner, by including this term in the Lagrangian. Keep in mind that this action is real with an I here and no I here. So there was a question earlier about why there's an I here and why, well, these I's you could move around sometimes, but this is a very standard notation. So if you vary this Dirac spinner, you get the very, very famous Dirac equation. This is the equation of motion for a 4-component spinner in flat space in 3+1 dimensions. Now, to simplify notation, you notice that the psi dagger gamma 0 always appears together. They appear together, so you usually define the psi bar. I apologize for the notation. This is how things go. This psi bar has nothing to do with that left and right while notation we're using, putting a bar over it. This has nothing to do with that. This is just a convention that's standard and people use. This is called the Dirac conjugate, and written in terms of the Dirac conjugate, this is what the action looks like. This action generalizes to other dimensions as well. So hopefully by now you realize that all I've done to write down this action and this variation principle, I intentionally set the Majorana masses to 0. I only kept the Dirac mass. That's why I call that term, that M prime Dirac mass. Give the other ones a different name. Recall that M prime was complex, right? So what I wrote here, actually, in writing this, I sort of assumed that M prime is real. I didn't say it loud, but I assumed that M prime is real. If you want to make it complex, because it was originally complex, you define this gamma 5. This gamma 5 is just some conventional thing. But look what it does. It's some object that multiplies the left by -1 and the right is left untouched. So now you could use gamma 5 to use these relations. And let me just jump ahead and tell you that your complex mass term, Dirac complex mass term, could be written in the following form, where these 1 plus minus gamma 5 are the left and right projections. These are these matrices. The way we constructed them sounded weird, but these are just like projecting to the left chiral part and the right chiral part. With that, I can write down the Dirac action in the following form with the complex mass, right? Here is the action I can write down. A useful identity for your homework or problem that you solve is going to be P left and P right with. So recall that gamma matrices send left spinners to right spinners and vice versa. This P left is a projection. And this is, so gammas basically send left projection to the right projection and vice versa. All right. Up to here, I assume that Majorana masses are 0. Now, can you put the Majorana masses back in? We said that Majorana masses can be included, these are M chi and M chi bar. Included, this is the term that we're dealing with, could be included only in special circumstances where you do not have such a symmetry. If you do have such a symmetry, if you want to have a U1 charge, then you're forbidden. But let's say you don't have the symmetry and you want to introduce add these Majorana masses in Dirac notation. To do that, you define this object called charge conjugation. At this point, you might be bored of group theory, but I can tell you that all of this work is going to pay off because the charge conjugation is an important, honest to goodness symmetry of our space-time that plays a role in what it does is swaps for particles and anti-particles. All that physics is coming out of this abstract sounding representation theory. And remember those epsilon matrices that I defined to upper and lower in this, play around with indices of spinors that seemed like arbitrary. Why was I doing that? Turns out that this charge conjugation operator is really diagonally written in terms of those guys. But if you want to know what it is in terms of Dirac spinors, it's just this expression. We're going to talk more about this in the next lecture because I feel I might have exhausted your attention span on representation theory. But in short, this charge conjugation operator allows us to include, we're going to see that in the next lecture, or hopefully in the next lecture, to include Majorana masses in the Dirac notation. And this is a symmetry that's very important, the symmetry transformation that's very important. It swaps particles and antiparticles. It need not be a symmetry of nature. Many theories have such symmetries, but it need not be a symmetry of nature. I haven't told you yet, but already I've actually, all this representation theory tells you that every particle in nature has an antiparticle. In terms of physics, this Majorana equation I was showing you is a spinor that is its own antiparticle. So these are things that we're going to work out. There's plenty of physics in all this representation theory. But let me summarize it. You're going to work out these things in your homework and get used to them a little bit more. It's a little bit nature of the spinors that they're a little bit calculation heavy. But let me try to summarize it to orient you a little bit better. So if you were taking a nap up to this point, perhaps it's a good point to pay attention for a few minutes because you're going to get a good recap. In summary, what did we do? We wanted to construct a representation theory of Lorenz group. We achieved that using a 4x4 matrices called gamma matrices, Dirac matrices. They satisfy the so-called Clifford algebra. The anti-commutator of these guys are two eta mu identity. There are 4x4 matrices for each value of mu. And mu happens to run off from 0, 1, 2, 3 as well. All right. You define, because these guys are 4x4, your spinors must be 4-dimensional. Such a spinor is called Dirac spinor. You split it, the two top upper components, you write it this way, two lower components, you write them this way. The Lorenz transformation, the generated Lorenz transformation in this notation is just the commutator of Lorenz gamma matrices with an I/4 in front. This is it. This is the summary of the whole representation theory, written elegantly in terms of Dirac matrices. So if you were to build representation theory of Lorenz group in other dimensions, your starting point is to find the Clifford algebra. Find the correct dimensional matrices that satisfy this algebra. Now, what's the equation of motion of such a field? The equation of motion, we wrote down an action for it. Here's the equation of motion for it. This guy is called, this is a mass. It's called the Dirac mass that I'm taking to be real for now. The 4 component was a Dirac spinor. If I take the right one to be the complex conjugate of the left one, that's called a Majorana spinor. If I take the Dirac spinor and apply the projection that projects the bottom 2 components or the upper 2 components, I get what it was called the Weyl spinors. Such a projection is only allowed as consistent if m prime is non-zero, is 0. This was the summary of it, right? So what did we do? We said representation theory. We took representation theory of 3 + 1 dimensions, and we organized these representations, and we discovered that we have a whole bunch of projective representations. These projective representations become spinor fields for us. The spinor fields, they came in pairs, left and right, and they're going to be having the interpretation of a particle and anti-particle. There is a charge conjugation operator that will swap these guys. Majorana spinors are the ones that are their own antiparticle. We're going to say all of that. And the Dirac spinor is generic. There's like it has a particle and antiparticle that are, well, there's a particle part, there's left and right that are independent of each other. And Weyl spinor are only left or only right. There was something that very important and crucial that happened here. The equations of motion, the dynamics of these modes were fixed for you by representation theory. In a sense. I wrote down equations of motion. That equation of motion has physics, it has dynamic law. Some might say that spinors don't have dynamics. Anyway, there's some sort of evolution law. Based on what? Based on locality. The only principle I used was locality. In the case of scalar field, what I get is second order in derivatives. So the equations of motion, the solution look like wave equations, right? Del t squared minus del x squared. That's like wave equation with a particular dispersion that we discussed. We're going to solve the Dirac equation and see actually the structure that comes out of it is fixed by locality and symmetry. So locality and representation theory fixed for you not only your matter content, but also the equations of motion. This is the magic of field theory. In quantum mechanics, you pick a bunch of particles, you know, like this spinor, that spinor, and you have to write down, cook up a Hamiltonian for it, right? There's no principle that tells you this is the Hamiltonian, nothing else. Here, for the free theory, this is what it is. This is it. It's fixed by representation theory, by symmetries and locality, it's all fixed. Field theory, locality, in particular, locality and symmetry are extremely powerful. All right, any questions? All right, I might have lost you by this point, but let me just say one thing, which is this is pretty much the end of our hardcore representation theory. And this is, the rest of it is going to be a lot of physics using a lot of these principles and discussing all of this. The next lecture is going to be about the physics behind all of this. What is a particle in field theory using representation theory? What's an antiparticle? What are these symmetries that we're talking about? And we're going to talk about spin and the connection between spin and statistics. And yeah, and I think that would be it for the classical field theory. After that, we're going to switch gear and talk about quantization. All right. So we're reaching the end of our discussion of classical field theory. All that's left is just telling you what is a particle. Once I tell you what a particle is, hopefully we can just go ahead and the remainder of the course will be quantization. All right, any questions?
In the middle of this page, the representation of Lorenz transformation in the Dirac spinor, on the Dirac spinor, there's an omega mu nu. So is that the representation of an infinitesimal?
Those are infinitesimal variables, yeah. So in writing a Lie group, in terms of Lie algebra, right, you expand around identity, and we had these theta k variables, remember? The k was an index that was running over the generators of the group. Here, that k is 2 indices mu nu, right? Why is that? Because it's lambda mu nu, right? Good.
Yeah, so this formula is only valid for infinitesimal transformations.
No. You mean this formula?
Yeah.
It's only valid for the components that are connected to identity. Because if your algebra, the Lie group, by exponentiating, you can move a long distance. You can move go really far. We haven't really explained this stuff in a sense, but you can use this to make larger transformation, but it's important that it's connected to identity. That's very crucial.
So given an arbitrary Lorenz transformation, how do I find out the representation using this formula?
Given what? Sorry, say it again.
Given an arbitrary Lorenz transformation,
Okay.
lambda, how do I find out the representation using this formula?
Let's say you're in 2+1 dimensions. There are 4 components to the Lorenz group. There were P and T, parity and time reversal, that were moving you from these different parts, right? If you focus on SO3, 1 plus, which is connected to identity, this is your representation. Everything else is this applied T and P. That's the whole O3, 1 group. This moves you around the connected part. Good?
Yes, thank you.
Sure. All right, any last questions? If not, thanks so much and have a nice day. Bye.
Thank you.